Hey everyone, my name is Muntazir Fidel, and today I'll be talking about STRIFs, which are architectural component diagrams that are meant to be used in the context of code reviews. So to start off this presentation, I basically want to remind ourselves of the differences between building software architecture and working a software project in comparison to other types of architectures found in the physical world. As Martin Fowler said, building software exists in a world of uncertainty unknown to the physical world. And the uncertainty he's talking about is in the form of changing requirements that software projects often have to deal with. Often, once you're done building the software, the requirements have changed considerably. And in order to adapt to these changing requirements, software architecture needs to be flexible enough to allow for that. And this is in quite contrast to physical structures, for example, like if you're building a bridge or a building, while the initial design is incredibly complex, um, a bridge in a building doesn't need to change its core structural components on a regular basis. So in order to maintain a high level of code quality, that allows software projects, again, just as a quick recap, to adapt to new requirements. And when we talk about code quality, we're talking about the quality of the code independent of features and bugs. So you can have code that is completely correct and it has no defects, but it's of low quality. And the reason why it would be of low quality is because it's not readable, it's not maintainable, and it's not extendable. Now, the most common process for maintaining code quality in a software project is through the code review process, which I'm sure many of us are already familiar with. But the basic idea is that a code reviewer protects the quality of the code repository from incoming code submissions. What I really want to draw your attention to is the artifacts that a reviewer typically uses in completing the code review. So the first is the source code, which corresponds to the source code of the original and the proposed code base. The second are continuous integration artifacts. So this would be the result of your static analysis tools and defect detection tools. And the third is a description of the code submission itself. And what I want to describe over the next two slides is the idea that the current tools that we commonly use for code reviews have a microscopic approach to the way they work. They look at the individual lines of code. The first example being line-wise diff. So I'm sure many of us have started doing a code review for a pull request in GitHub, and we're presented with a similar type of view where we have a list of files that have changed and a list of line-wise diffs. And the question I want to ask right now is this the best way to start a code review? In my opinion, with any decently sized code review, looking at all these lines of change lines of code and these files that have changed, it's overwhelming and it's too much information. And perhaps a better way to approach this would be to look at some higher level context or some macroscopic view of code. And what I mean by a macroscopic view of code is a view of code where there are certain architectural properties about the system that you can analyze that aren't directly manifest in the code itself. Another common tool we use during code reviews are obviously static analysis tools. So what I have on the screen is a picture of the SonarQube static analysis suite for Java programs. And as you can see, they've organized in the tabs near the middle of the screen, the issues they find by vulnerability, bug, security hotspot, and code smells. And some of the code smells are, for example, methods and field names should not be the same or differ only by capitalization. Again, the focus of these static analysis tools, in my opinion, seems to revolve around microscopic problems with the code. And again, I'd ask a similar question that if you were working in an enterprise system and you ran SonarQube and it had no vulnerabilities, it had no bugs, no security hotspots, and no code smells, would you still be confident that that system is readable, maintainable, extendable, adaptable to new requirements? And I think the answer, in my opinion, is while this would say a good amount about that answer, and it would be, and it's definitely a minimum, you at a minimum need static analysis tools running, it wouldn't say a lot because you can still have really poor design at a macroscopic view of the system and really poor interaction between components, and it would still make maintaining and adapting to new requirements a nightmare. So in terms of doing code reviews, hopefully I've been able to convince you that majority of the tools we use are microscopic in nature. And if reviewers want to do a macroscopic assessment of incoming code, there's two real options. The first is many reviewers might not even do that type of review. They might not even assess the design of the incoming code submission. Or the second option is that they maintain a sort of mental model of the architecture of the system and how the different components are interacting. And this places a large cognitive burden on the code reviewers, which slows them down and makes the overall process a lot more difficult. In terms of existing solutions to this problem, I just want to quickly run over two that are related. So the goal behind DesignDiff and LSDiff, there are two existing tools and research that has been done in them where they try to identify high-level structural differences between a proposed and incoming code base. And what they do is they output the changes that occur in a textual format. And I think, again, the room for improvement in these tools is that the output is just a textual format of what has changed. So class A now implements class C, or implements, interface C, and perhaps method A now has a new parameter. But this is not consumable from humans very easily because, as I'm sure we'd all agree, diagrams and visualizations are the best way to simplify complex architectures and complex systems into a more consumable and readable way. So now I'm going to demonstrate what these Striff diagrams look like. And on your screen, you can see a sample Striff diagram. Again, they're designed in a way to help replicate, or at least come close to, the original lens that the architect of the system might have used when designing the system. And they use a lot of the properties that line-wise diffs in a regular diff on GitHub that you might have as well. So the coloring scheme is probably the most obvious. If I look at all the things in green, those represent components that are entering the system as a result of the code submission. All the entities that are in red represent components that are exiting the system as a result of the code submission. And we've introduced a new coloring scheme in blue, which represents components which are both in the existing and proposed system, but their underlying implementation has changed. And we felt that was important to include because from the point of view of the code reviewer who's trying to figure out where to get started in this big pull request, he or she would want to understand not only what components have entered or exited the system, but also what components, perhaps their underlying implementation and algorithm use has changed. And that would be valuable information as well. The other aspect we've included in these diagrams are documentation. So in our understanding, usually documentation for high-level components like interfaces and classes should only contain what that class or interface is and how it works, but nothing about its implementation. And so this becomes a natural place to put documentation like this, especially when you're someone who's not familiar with the code base, to quickly get up to speed as to what the responsibility of these components are in the context of the larger system. And as we'll see later on in the algorithm, we also place constraints on the size of these diagrams, but we'll get more to that later. The last thing I want to quickly point out is if you look at any diff on GitHub for a set of change lines, GitHub at least will also include three lines of context code before and after any lines of change code in order to provide context to the lines of code that have changed. Similarly, in Striff diagrams, we have components that have changed, like available options and the class command line options, but we've also included components that have not changed, like this interface called class name filter. And these context components are essential in understanding the components that have actually changed. How we generate context components is going to come next as we describe the algorithm. So the algorithm that we use to generate Striff diagrams there are really 4 stages to them. The first stage is really to parse the source code. So we have an original code base and we have the proposed code base that represents the original code base with the incoming code submission. And what we do is we parse each of these code bases and collect a list of components or high-level components that correspond to classes and interfaces, and these will form the building blocks of the Striff diagram as you just saw. And each component in this collection is represented as a high-level filtered down AST. in the sense that in the original code base, you would have a class with children of fields and methods, and that structure of fields and methods being children of the class overall would be reflected in this AST structure inside each collection. Stage two is to generate the graphs. So now we generate a graph where the vertices correspond to high-level components in the code base, and edges correspond to the UML class relationships between components. So you could imagine that in the original code base, if class A implements interface B, then in this new graph, we have two vertices that represent class A and interface B respectively, and they're connected by an edge, which has a weight of 6. And the reason why it would have a weight of 6 is because we're weighing all the edges in this graph according to the importance of the UML relationship that exists between the connected components. Now, the weighting we've used here is very interesting. Basically, what we've said is that from an architect's point of view, from someone who's trying to understand the object-oriented properties of this architecture, these relationships are more important than other ones. So we'd be more interested in understanding the interfaces that are implemented and the classes that are extended versus simple association relationship between components. And all of this is subject to, of course, further research. We've come up with these values based on an initial best estimate, and we're hoping that in the future we can iterate over these values by getting feedback on the diagrams itself. So now that we have these two graphs, GO is the graph of the original code base and GP is the graph of the proposed code base, we now essentially diff them together and we have a merged graph that represents both of the code base merged together, except there are now components in this code base that represent components that are exiting the system. And there are other components and relationships that represent components and relationships that are entering the system. And while this is not the last stage of the algorithm, I was able to output the graph represented by GM in a sample diagram just to give you an idea of what it looks like. But as you can see, the output of stage 3 is this really large diagram represented by that merged graph. And as you can see, it's not very readable at all. We certainly wouldn't want to show anything like this to a code reviewer because it would just make their life even more difficult. But as you're probably expecting, the next stage of our algorithm is to try and take this really large graph and break it down in a meaningful way. And this is a really difficult problem. Often many automated solutions for generating or reverse engineering UML diagrams have failed because diagrams were either too large or too big or they weren't related. And we're hoping to use a unique algorithm in order to solve this problem. And the way we do that is by applying a community detection algorithm over the graph. So we use the Louvain algorithm to produce subgraphs that maximize edge density with respect to other graphs. And what we do is recursively run this community detection algorithm over that original graph, that really large original graph that you saw previously, to eventually produce diagrams that are, number one, small enough to be readable. So we can dictate that perhaps we're interested in only seeing graphs that are 6 to 7 components size. And so we can continuously and recursively execute the Louvain algorithm over that initial subgraph or initial graph to get subgraphs that are approximate to 6 or 7 in size. Number two, it produces diagrams that contain logically related components from an object-oriented point of view. And the reason why this is the case is because of the weighting scheme we used initially. So because we're weighing different edges according to the UML class relationships they represent, you can imagine this graph with vertices that correspond to components and edges that are weighed according to the importance of the relationship between those two components in the original code base. Because the Louvain algorithm is maximizing edge density within neighborhoods, what it's actually doing is finding highly connected components from an object-oriented point of view and displaying those graphs to the user. So now you're not just picking any sort of components that are connected to each other, you're using a weighting scheme to inform the community detection algorithm to produce graphs that are more logically connected. And lastly, we get diagrams that show essential context along side modified components. And that's for the same reason as mentioned in point number 2, that we're weighing edges according to the UML relationship represented between those components. And so when the Louvain algorithm runs and generates neighborhoods and subgraphs, they contain a lot of highly connected components in the same diagram. So this entire algorithm is implemented over 2 Java libraries that I will link at the end of this presentation, and they're available on GitHub. But what I've done is I've hosted and ran these libraries as an API, as a REST API, and built a Chrome integration that integrates with GitHub. And so what we're going to do now is we're going to actually be able to generate Strift diagrams on the fly looking at pull requests on GitHub. So I'm looking at JUnit 5 repository again on GitHub, and there's a pull request open here. I chose the latest one, and basically there's a whole bunch of commits here. Again, if I go to files change, it's just an overwhelming amount of information, as you can see. We could go through these lines of code, and it'd be very difficult to piece together what all of these do in the context of the goal of this pull request. And so again, all of this information is quite overwhelming. So so what the integration does is it adds a button on the actual GitHub website that when you click on it, will open a new tab that contains Strift diagrams for the pull request you were looking at. And it generates a set of diagrams. As you recall, in step 3, we have this really large set of diagrams that cannot be read by any sane person. So the result of the Louvain algorithm is these subgraphs you can see in front of you. And what it's doing is, again, it's using those weighted edges to produce smaller graphs and diagrams that represent more readable components of the overall architecture. And the idea, again, behind Strift diagrams is really to guide the code review process. So as you figure out what the components are doing at a high level, you can decide then what you want to investigate at a line level, and then go back into the pull request and look line by line in the questions or aspects of the code review that you want to investigate. And I think, in my opinion, informs a more natural way to start doing a code review and to get an understanding of the macroscopic impact of the incoming code submission. And so in terms of current state development, right now the tool supports Java and Go. And if you want to stay up to date with developments, obviously this area of research is huge because, like a lot of the initial values, we configured by hand. But what we're hoping is by expanding and making it available for people to use in open source projects, we'll be able to collect more information, more opinions on how the tool works. And so you can go to www.strift.io to stay up to date with the latest ways to consume Strift. So the main way to consume it right now is the Chrome integration that I demoed today, which is available on GitHub, and soon it'll be published to the Chrome Marketplace. And eventually there are plans to develop a GitHub action. So as you add commits or push commits to a branch that's involved in an active pull request, the action would take care of commenting to that pull request in GitHub with the latest set of Strift diagrams that are relevant to that pull request. And that's the end of my presentation. Thank you very much.
Thanks a lot. It's very interesting. Well, to me personally, as I'm a developer, so I would love to use that tool. So I have a few practical questions. The first one is, it seems that this tool has to have access, at least read-only access, to the repository entirely, not only the pull request. I mean, not only what we see on the web page, right? So you check out the whole code.
Yes.
Okay. Understood. And second, this integration now it's done on Chrome, but is it possible in general to integrate it with GitHub somehow? Not as an action, but to make the button there. Is it possible? Because now, as far as I understand, you just inject it into HTML page, right?
Exactly, yeah. To the best of my knowledge, I don't think that's possible, just because that would be controlled by GitHub. So I think the only way you'd sort of do it is the way I did it, which is inject a button or use GitHub Actions. But there could be other more like native ways to do it.
And did you try somehow to validate, validate your approach, like make some experiments with large amount of pull requests or code lines, something like that, like big numbers? Do you have that, or you just personally experience the result, and that's it.
Yeah, so it's personal experience, and about a year ago, we reached out to a number of development teams or open source projects on GitHub. We got response from a handful of them, and actually, a lot of the modifications we've made in terms of the diagram size, for example, was a reflection of some of the conversations we've had with them. Um, I think going forward, a good idea was to look at the use of these diagrams and how they could support refactoring patterns and stuff like that. But really, this is the whole idea behind really presenting at this conference and publishing it as a Chrome integration. We can start collecting data and start asking people about their experience and really start to validate if this is a valid approach.
And what do you think is the next step? Like, how can you make this tool, more and more interesting for developers?
Yeah, so I think the first thing is to get more metrics and data from people on how they use it. I think there's definitely a gap that I mentioned in the presentation, whereas the current tools we use for code reviews are microscopic in nature in terms of, they definitely have some element of assessing design and class dependencies between them. But I think the reason why we're not using static analysis tools solely to do code reviews and we still have that human element is because humans are doing an aspect of design, which is like a creative process. And so there's definitely a gap there. And I think in order to progress Strifts, in order to fulfill that gap, it's more research in terms of what humans want to see, like what are they actually looking for from a design perspective when they do code reviews, and how can we help give them the information they need through these diagrams.
And is it possible from your diagram to click and get back to the code?
That's
to
something
the line?
No, that's definitely something we want to support in the future. So exactly that, the idea where you click on method and it'll show you the code. That's something we're working towards as well.
And maybe it will be also, maybe you just mentioned it, but it will be possible in the future to somehow label the changes or make them some make some conclusions about what was done there. So instead of just showing me the diagram, but saying, for example, the singleton was removed and the factory method was introduced, something like this.
Yeah, I think one of the things I was thinking about recently was incorporating commit information in the way we split the subgraphs. So right now we're just looking at the relationships between components and what type of UML relationships exist. But you would think that if a pull request has multiple commits and that person has organized the commits in a certain way, the fact that that person chose to include these changes in this commit would influence perhaps how you'd want to show those graphs to the final user. So I think there's so much more we can look at in order to develop more useful graphs and to take it to the next level. Yeah.
Don't you think that GitHub is doing very similar or maybe exactly the same research right now?
Yeah, they are. Definitely, yeah.
I think they should, because they have all the information and they
Exactly.
definitely are also concerned about this problem.
Yeah.
And do you think, what's your opinion about there are two different theories in the world. One is saying that large pull requests are better because they include all the necessary changes and they represent the entire solution. While the other theory is saying that it's better to use smaller pull requests because they're easier to review, even though they introduce only partial solutions, but they're easier to review and easier to merge. So which side are you on?
Yeah, that's a difficult question. I think at the moment, I think the problem with the large pull requests is that there's not good enough tools to support it, right? So ideally, I think it's the right solution, but the reason why most people gravitate towards the smaller ones is because it's a lack of tooling support. I think it's the same problem when we talk about like monolithic repos versus keeping repos like separated. There's a lack of tool support, so we include everything into a monolith, and I think this is one of those examples. That's actually one of the reasons why we take that original graph and we have to use a community detection algorithm to split it up. Technically, if you're in a very disciplined engineering team, your pull requests are quite small. And so you wouldn't even need to, like, you could just get one graph all the time, one diagram all the time because your pull request is small. But of course, that's very difficult to do and probably not the case in 95% of teams. So we have to work with that.
Right. A question from one of the listeners. Can this tool also be extended to help software developers to solve conflicts between two commits? Merge conflicts, I believe.
Yeah. It's not clear to me how it would be able to help with that.
So let's say, well, maybe I can imagine that. Let's say I have the merge request and I see the merge conflict, so I cannot merge it. And then I open the diagram, and on the diagram, I see like red places which show me where are the conflicts.
Okay.
And then I somehow visually understand, okay, there are the problems, and I go there.
Yeah, I guess it could be adapted to support that. But that's probably not something we would look at doing right now, because I think there are a lot of really good tools for merge conflict and handling those type of problems. So
And there's another question. Any plans to support just Git? Perhaps generate diagrams from the CLI? Oh, I mean, they're talking about without GitHub,
yeah,
just
without
Git,
GitHub.
command line, yeah.
Yeah, again, because it's a research phase, obviously the thing we try to do is what's easiest, and GitHub has extensive API and is used by most people. But like if the tool kicks off and it becomes more popular, again, it's open source, then obviously there'd be more support to expand to just regular Git and maybe other types of version control. At the moment, we're just focused on GitHub.
Because there's the extension of this question. They're saying that they use a different tool for merge for pull requests. They use Gerrit. Probably you know about it.
Yeah.
And yeah, it's a different story.
Yeah, again,
So-
because it's a research phase, like the introduction of that Chrome integration is we're just trying to make it as easy as possible for the largest number of people, so we can get the biggest amount of feedback. I think.
And what do you think? And what do you think is your core innovation in the whole project? I think this is the mechanism, the method of minimizing the graphs, or not?
I think it would be minimizing the graphs, and I think the other idea is it's very simple, but it's really taking this idea of line-wise diffs and applying it to a macroscopic view of the code. I think those two are the main contributions. Like it's really simple, but I think as useful as line-wise diffs are, like everyone looks at them when you do a pull request, I envision Strift diagrams from an architectural point of view being as important as looking at line-wise diffs, hopefully some point in the future. Because if you think about it, they're both doing something very fundamental, but at different levels and at different views of the code.
Okay, my final question. How long did it take, this project?
So I've actually been working on this idea for the last 2 to 3 years in terms of the actual tool itself. So yeah, I'd say 3 years.
And now it's open, so anyone who is watching this presentation, they can use it, right?
Correct. Yeah,
Okay.
just visit strift.io, and it has all the information to go to different repositories that are used, and you can also subscribe to stay up to date with whatever new things that are coming out.
All right. Thanks a lot.